Okay, so I guess that all these techniques, like this Lindell technique, is to get it faster by a constant based on the simplest possible majority case, and the constant is roughly 3. I think. So with the simple the majority cuts and choose, you need to do 3 times more circuits than with the super tricks from Lindell. That's my understanding, at least. So I guess I'd be much more interested to thoroughly understand the most basic version, which is the one where you use majority, than the super optimized one.
Mm-hmm. Yeah, I could share my screen. We can through the summary maybe.
Mm-hmm.
Just feel free to write in it as well if you want. Anyone?
Meanwhile, one question: does anybody have insights on why that probability is actually exactly 2 to the power minus 0.311 times s?
It's a combinatorial problem, I guess. So you've got like n circuits, you reveal part of them, and provided that they are all correct, what's the probability that all of them were correct and also the majority is incorrect? And I guess.
But I presume that this probability, well, maybe I'm wrong, but this probability should then depend on the number of samples taken from the entire set.
Yes, and I think they just take like the best number of samples. I mean, this is yeah.
So S is number of samples, not the decided.
No, S is number of circuits, and they always take optimal number of samples, which they don't say what it is, but probably something like 60–70%.
Like half of them or something. Well, okay. Well, I'll try to dig into this. Thanks.
I mean, the answer is probably that they take half of they sample half of them, and the only chance for the attacker to actually succeed is to make to also choose half of them to be incorrect, and then you need to exactly sample these correct ones and as the ones you check.
No. Attacker could make like 60% of them incorrect. So when you sample 50%, they are all. Oh no. So okay. I understand. So attacker could make 40% of them incorrect. You sample 50%, they are all correct, and the majority of the remaining ones is incorrect.
No, it's not about majority anymore, because he explained that in using his bootstrapping, in order for it to succeed, all the circuits you check need to be correct, and all the circuits you don't check need to be incorrect. Sorry, this is in order for it to fail. This is the only possibility.
Sure, this is using the Lindell trick, but I think 0.3 was before the trick.
Yeah, sure. Then you just need some Chernow bound, right?
Something like that.
Well, maybe this deserves another time for discussion.
So what's in the book? I didn't look into that. Are these mostly optimizations similar to Lindell, or?
That one is mentioned, yeah. Yeah, I mean, I can go through this document quickly. It's because that will explain the book if you haven't read the book. I mean, they explain the cut and choose as a game as well, abstractly, which is maybe a bit easier to understand if you remove like the goblet circuits part. So the game is you have 2 players, okay, P1 and P2, and P1 generates P balls, small P balls. and the balls are either red or green. And red would signify sort of an incorrect garbled circuit, and green would be a correctly generated garbled circuit. And so P2 can choose a random subset of these balls and check them. And so if any of these balls are red, so were created incorrectly, then P1 loses. That's the checking phase. So this would happen sort of if you open the garbled circuits, C of them, and you would inspect whether or not they are incorrectly or whether they are correctly wired up internally. So if that check is okay, you can move on to the evaluation, and then in garbled circuits, P2 would evaluate the remaining garbled circuits. And now if the majority of the unchecked balls are red, then player one would win. Or in the Lindell version, you can also, you can also have it so that if all the unchecked balls now are red, the player one wins. So that's the cut and choose game. Is that clear, or you don't have any questions?
I think it's pretty clear.
Yeah. In the book, they also talk about batching this game, and so that's quite useful, as they explain in the book. But what you can do is, if you evaluate the same function n times, you could, for example, batch this game. So player one would generate n times p plus c balls or circuits. And here n is the number of times you want to evaluate your circuit, and c is the number of times you check random balls from random circuits that are generated, and p is just another security parameter. And yeah, so you do player one player two chooses c of these n times p plus c balls to check them. If any of them are red, then he knows that P1 cheated, and so aborts the protocol. Otherwise, in the batching, P2 assigns the remaining balls into n buckets, so that each bucket contains P balls. That is, P2 assigns all of the circuits into n different buckets, and then evaluates the remaining buckets. So each bucket as a circuit with with its inputs and outputs. And if any of the buckets contain a majority of red balls, or if any bucket contains only red balls, then player one would win. So that's
I don't know what's the proper relation between P and C. It looks like this optimization optimizes things by a constant only, I think.
The relationship between P and C.
Yeah. To get like a reasonable bounce, because like intuition would tell me that this optimizes it by a constant factor only.
Yeah, this will be always constants only. But what I am wondering now is, like, how does it relate to the real problem we are trying to solve? How do you know that it contains red balls in this last step? So what you see, I think, when evaluating circuits is that there is some majority, but you have no idea whether this is majority of red balls or of
okay, so you mean in this step?
Yeah, I mean, you do not know that P1 have won. You never know. It just, you just compute the probability. What's the probability that P1 is winning? But if you're P2, you'll never know that.
So exactly, if you only take the majority in the garbled circuits cut and choose, you would output the majority value from all the circuits in this step. So you wouldn't know if he cheated, or you would know he cheated by you still have to output.
You will know he tried to cheat, but you wouldn't know whether he succeeded or not. There is a very small probability that you would not even know that he tried to cheat if all of the balls were red.
But this is different now to, I think we can cover the case later when you're only looking at if the bucket contains only red balls. Okay, so that was the Lindell strategy. So in that case, you know he cheated, and you can also prove that P1 cheated. And I have it further down in the document. So, but in this step, in the checking step, you can prove that he cheated as well and abort, because you haven't really leaked any inputs yet. So it's safe to abort at that point.
Yeah, sure.
May I ask you a question? I think I missed probably something in the very, very beginning. So how does P2 distinguish between correct and incorrect outputs?
He does not. He only checks whether all the outputs are the same or not.
Okay, thanks.
He will never know which one is correct one.
Makes me feel better, thank you.
Yeah, that's the same question I had actually. So in the real game, he will not know whether the ball is red or green. He will only see that they have different colors.
So he will not know the result of the game, whether he have won or not.
No, not only that, he will not know.
Only that.
Well, so in the evaluation, you will not know, but in checking you will know.
In checking, you
know, yes.
But not in evaluation.
And in evaluation, you will evaluate something. And this probability you will compute in this game is the probability that this something will be a correct output. If it will be not, then well, you will not know about it.
So basically, the checking process is denoted by what? By comparison of the actual circuit against some.
So you decrypt the circuit essentially. So garbling means kind of encrypting, and you ask the other party to actually decrypt it in the plane. So you will not use it, but you can check if it was encrypted correctly.
Yeah, actually, there are some technical details here. So I assume there is this concept of masks in these garbled circuits. So I assume that all of the circuits needs to be the same kind of when it comes to masks. So if they are all the same, then the outputs will be the same for each of them. So now
masks is only like one detail in implementation. You don't need these masks to do garbled circuits, but it's then less efficient only. So this is
okay. You're correct. You just you can just kind of encrypt the results, and that's all. Okay, that's correct. So you can just have like identical circuits using different keys, and you can open only the chosen part of them.
By saying different keys, do you mean extra redundant inputs, for example, of that circuit?
No, the circuit itself, the idea of a garbled circuit is that there are encryption keys for each of the.
Of course. Yeah. Thank you.
So when like you reveal only the keys for the circuits to be checked, and you check them, and you will never reveal the keys for the remaining ones. So like general note would be that provided that even the normal, like the garbled circuit before were pretty slow, so these ones are like whole degrees of magnitude slower.
Yeah, I guess a factor of, what did he say, 120?
Yes, factor of 100, something like that.
Yep. Yeah, but there are some more tricks. So I hope it's quite clear how to use it in garbled circuits.
I think it's pretty clear,
yeah. Exactly.
Yeah, sure. That's, I think, also pretty
input consistency is not super interesting. But
What does it even mean, input consistency?
okay, so the cut and choose, as Lindell argued, the cut and choose protocol only you ensure that the garbled circuit is correct, but you still don't know if P1's input is always the same every time you evaluate, and that P2's input is always the same when you evaluate. Okay. So, for example, during the evaluation step, let me go up here. During the evaluation, or here rather, P2 can, for every like different garbled circuit, P2 could use a different input and learn things about P1's inputs as well. And P1 could also use different inputs to these circuits. So we need to have other strategies to ensure that as well.
So this is pretty much required for any version of this cut and choose trick to keep it actually maliciously safe.
Yeah, but ensuring that P2's inputs are consistent is actually quite easy, right? So P2 is the evaluator, and if you remember the garbled circuits, how it works is that P2 chooses his inputs using oblivious transfer with P1, and the strategy you can employ is that for every oblivious transfer, instead of transferring only one input for one of the circuit, you transfer like the batch of inputs for the group of circuits, so that they're consistent. So that's how you can do it.
How about P1 consistency? I guess it's a trigger, some commitment thing should be done probably.
Yeah, so P1 that's the tricky one. They had one example in the book where you commit to, so P1 has to commit to his inputs beforehand with this random 2 universal hash function H that P2 chooses. And then both parties evaluate the garbled circuit using cut and choose to ensure that it's consistent, and they evaluate this garbled circuit here that computes the function, but also the hash function within the circuit. So you have some kind of bit of overhead as well.
So you augment the circuit with some additional thing just to check for
consistency.
For consistency.
So exactly. So doing this, player one doesn't have to reveal his input, but rather securely it computes the commitment or the hash value of P1's input and the random seed it chose. Yeah. So
this is a general technique, right? It doesn't need to be applied to garbled circuits. It's just general for multi-party computation.
Mm-hmm. And the other strategy is this Lindell thing, which they call input recovery technique. So it has to I'll start off by how it works loosely, but we just saw it. So P2 evaluates the circuit, and if any two outputs in the circuit differ, then P2 can force P1 to share its input. So what this means is that player one, before the protocol sort of commits to its inputs to some kind of input recovery functionality, and later on, if P2 presents a proof that P1 cheated, then P2 gets all the inputs from P1. So so this way, we can also ensure input consistency of P1, and also ensure that we don't have to output the majority. Rather, we can, I think, always abort. Right? That was if P1 cheats during the evaluation.
Oh, I think it's the other way around. We always deliver the result, and it's always the correct one. Although sometimes
exactly,
we have it like kind of illegally by getting P2's input, P1's input.
Mm-hmm. Yes. So this is, but it's quite a, I mean, the details, there aren't that many details in the book about it, but yeah.
Still, comparing to the previous technique, I think it's not a big improvement, because the previous one where you augment the circuit also, I mean, the augmentation of the circuit is independent of the circuit size. So it's also just a constant factor, the SS11.
Yeah, but I think the difference is,
although you need to compute a hash function, so circuits, it's a constant factor, but circuits for hashing functions are actually pretty
but I think the difference was that, I mean, because you can you only need to, like, if you don't need to have a majority of correct values anymore, so but rather in the evaluation step, and so you can adjust your parameters, the security parameters, accordingly. So I think that gives you some improvement.
Oh, okay. So this gives improvement and also ensures P1's inputs are consistent, like for free.
Exactly. So I think that instead of this 3.12 lambda thing, it's just lambda that you need to choose for P in this case as a parameter. And but there's another thing in the book that's quite interesting. It's continuing with the batched cut and choose. So I think this is similar to what we had last week, or last week, whenever. That well, instead of doing cut and choose on circuits, you can do it on gates. Okay, so it's this protocol called Lego where they present it, and what you do is the player one generates loads of gates, and then player two, chooses a subset of these gates that player one has to reveal, and then if any of these gates are are bad, then player two knows that player one cheated, and then player two, in the next step, in the evaluation step, player two chooses or assigns buckets to each gate, and each bucket sort of represents a gate in the circuit. And so it's sufficient if a bucket has a majority of correct gates. And I mean, the benefit of this is that you don't have to batch the same function multiple times. You instead you do the batching over the gates. So you
but
sort of have
you need to batch each gate multiple times. So I don't really see the gain here.
Well, I mean, if you want to only compute the function once, then you can't really batch on the number of function executions, right? So the difference is here we can batch still, even if we only execute the function once.
Sure. So you can get this constant factor improvement which batching gives, even if you compute the function only once.
Exactly. Yeah. And if you do it multiple times, it's a bit more optimal, so to say. So
okay, but this is a clever technique indeed. Although all these techniques here, they seems to improve the basic idea like by a factor of, I don't know, 5 in total, or probably something like that. Like if you get batching and Lindell idea together. So that's still like you need 50 circuits or something like that. I mean, it's 50 times slower than semi-honest case, or I don't know, 20 times slower or something of that order of magnitude.
Yeah. It's
and I think the test, I don't know, recently we've seen, oh no, we've seen the test results for malicious case actually from the scale Mamba, which is maliciously secure. So, okay, that's why it's so slow.
yeah. It's, but it's a technique, you know, maybe it would have been good to read these sections a few weeks ago. I mean, I think we've seen them a few times, these techniques, just without proper study. So.
Indeed, I mean, it's a nice, I guess, closure to the whole design. It would be nice. I mean, I don't know how to do it. Perhaps this marble circuit do it to have a technique where, like, the control flow of the program is using garbled circuits, like all the ifs and things like that, and then the actual computation, which usually involves numbers, is done by private arithmetics, meaning this secret sharing kind of MPC. So then you would have several rounds of this protocol, but yeah, it's pretty hard, I guess, to have a control flow using only multiplication. But I do not know much about it. I guess some people are exploring that. Okay, so there are a few things left in the book. Most of them are also kind of constant factor optimizations. I found, like, looking for this talk, I found a talk which is an hour long, and it's basically on garbage circuit optimizations. So there's like freak SOR gate, which was mentioned several times, and we haven't looked into that, and some similar tricks. So we could explore that next week, for example.
Yeah, sounds good. Should we decide on what we explore?
I mean,